The Best of Our Knowledge explores topics on learning, education, and research. Coming up, shape-shifting, fluid-like robotic materials may one day no longer exist only in science fiction. We'll learn about how microplastics could contribute to antibiotic resistance. And students and faculty ask questions over cuts to federal funding for college campuses. I'm Lucas Willard, host of The Best of Our Knowledge. You're listening to The Best of Our Knowledge. I'm Lucas Willard. Miniature robots that can arrange themselves to function as a shape-shifting material sounds like science fiction, but our next guest worked to prove such technology is possible. Matthew Devlin, a former doctoral researcher at UC Santa Barbara, studied simple robots that could be programmed to function as a fluid to form a solid structure. I spoke with him to learn more.
So the idea is it would be really, really cool to have some sort of programmable synthetic material that kind of it can sculpt and do all sorts of crazy things. So if you think of like, imagine you could have a wrench and suddenly you wanted your wrench to be a screwdriver, or you wanted this material that could change its shape. And so we kind of look around at biology and other like facets of science and think, where does this sort of thing exist? And we saw that in embryos, they can kind of go from being a big blob then to turning into a person. And so kind of that embryos are kind of a magic material, and obviously they're, infinitely complicated. So is there a way to kind of distill embryonic principles down to robots so we can start to kind of recapitulate some of those functions that embryos can do in these developing tissues, specifically the mechanical properties like, growing or changing shape or supporting structures, like you have to build bones and things. And is there a way to kind of distill that and put that into robots or something engineered that we can control?
So it almost sounds like science fiction. And I think we've all seen a Hollywood movie where you have a superhero or an alien or the bad guy, and there's a fast
Yeah,
changing
absolutely.
transformation going on. So it sounds like it's almost born out of those ideas. Um, but when you actually look at these, the robots in the proof of concept, how large are they? Are they small? Are they very, very small? What can you tell me
So
about the individual units themselves in this research?
right now, so you're absolutely right that it's kind of born out of this science fiction idea of like a Terminator 2 or like a Big Hero 6 or something. But we didn't know what kind of science we needed to make that work. So we wanted to make our first proof of concept as something that's easy for us to prototype and to experiment on for the physics. So right now they're about 4 inches across. They look like really thick hockey pucks, basically, and so they can all sit next to each other on a table or kind of on an inclined plane, or even kind of stacked just vertically. And they can push and pull off of each other. So they have these little gears on the sides that allow them to touch each other and make contact. And then they have a big circuit board on top that lets us talk to them through light specifically.
How different is this in concept than a drone show where you have multiple small little machines that are sent a signal and they can arrange themselves into a shape in a drone show in the sky with a light on it?
Sure, yeah, I think that's actually really important because there's lots of kind of robot work of you see these drone shows now that have 10,000 drones in the sky, or there have been lots of little micro robot projects too that have lots of drones or lots of little robots. And I think a key distinction here is that we are not talking to every individual robot. Like they can't talk to each other. All they know is that they see a light source, which we're just telling them a direction. So in an embryo, you know which way your head is and which way your tail is, and there's like a chemical that's being secreted that tells you which way is up, essentially. Um, and so that basically all we do with the robots is we tell them which way is up, and then they all kind of naturally apply this pattern, and they can line up in a single line. So I'm essentially controlling them with a flashlight. And so I just send them one signal, a light signal, and then they can all magically kind of line up in a single file line or line up however I choose, which is different. So in a drone show, you have a big computer at the base, and it's telling every single drone where to go, and the drones are telling the computer where they are and where they think they are, and where their neighbors might be. And so for us, the robots don't know anything. They just know that which way is up, essentially, and they kind of naturally form these lines and things.
So, therefore, it might be if the robots had power, then they could react on their own in a way if they were if there was an external stimulus, a change in light, like you mentioned, and then the robots would be able to do what they're programmed to do to arrange in a certain pattern or array. Is that what you're saying?
Yeah, so right now, it's just me telling them which way to go. I hold the light and tell them to form a bridge, or there's a one case where I put them in a pile and then I stand on them, and I'm a 6 foot tall man, pretty heavy. I stand on them. They can support, let's say, 80 kilos of weight, and then I step on them and then I walk away so they can hold that entire force. And then I apply this light signal and then they kind of fluidize and they behave more like a liquid and they can flow to the sides and make these piles. And so all they know is, okay, the light is on. I need to uh, turn my gears in a way that makes us a fluid, and then they can kind of collapse into a small pile.
So for something like a tool to change from a wrench to a screwdriver, this is something that would need to be shrunk down in scale quite a bit, correct?
Correct. And so right now, I would say it's the scale we currently made, it is 4 inch wide, is just for figuring out the physics, but the physics is actually the same as the embryos. So those cells are 10 microns across and going up or down. So you can make a car-sized one, or you can make a biological cell-sized one, and the physics is going to be the same. And so right now, I think that with current technology, we could pretty easily make robots that are about 20 millimeters or 2 centimeters across, or like an inch wide. Um, it would be pretty easy to do, and I think even that would give you some really cool features. Obviously, you can't make a screwdriver, but you could make a really big wrench, or you could make some of these scaffolding and bridging supports. I think to get even smaller, there's a lot of work within micro robots that making these truly microscopic robots, and it's very hard. But I think physically, all of the physics is there that they could make something like this.
So, what are some of the other applications beyond a bridge, like you had mentioned, or a screwdriver?
Hmm.
What are some of the applications that you think might be able to one day um, involve these robots and this concept?
Yeah, I think of it really as kind of the ultimate Swiss Army knife of, let's say you were on the space station or you were somewhere that had limited resources, you could have this kind of bucket of robots, which is kind of this big, grand challenge question of, could you have a bucket of stuff and then you can tell it, hey, make a tool, or could you make a chair, or could you make, whatever you wanted. So if you kind of think about 3D printing as you have a spool of material and you can kind of print whatever you want. Well, what if the material itself could take any shape that you wanted? And I think it fills a very similar use case of, well, you have this really strong material that can change into whatever shape that you want, kind of whenever you want it to, and it can do so on the fly, which could be really useful, I think.
Yeah, and Matt, now where is your research taking you, and are you exploring this concept at all in your professional career?
So I'm not currently working on this. I'm actually making pharmaceutical instruments. So lots like a fully separate, doing a lot of the mechanical engineering for that and really honing my skills on how to manufacture things and how to scale products up. One thing I think that this work could do pretty readily is I think that we've essentially made a hardware platform that other researchers could use to do the programming on. So for instance, if you applied artificial intelligence to these robots and you made them a lot smarter. So right now this is their dumbest form. It would be really hard. You can't really make them any dumber. And I think there's just a huge potential for the types of work that you could do on these robots. And I'd be happy to support anyone, answer questions or anything like that for people working on this in the future. Um, but right now, I think there's a hardware platform that exists for people to try their programming or algorithms on. And I think there's a lot of potential there.
Well, Matt, thank you so much for taking the time. Again, I appreciate it.
Awesome. Thank you so much.
Matthew Devlin's research is published in the journal Science. You're listening to The Best of Our Knowledge. I'm Lucas Willard. On Earth, microplastics are nearly everywhere. Microscopic plastic particles could impact our health, and a new study finds that they may even contribute to antibiotic resistance. The best of our knowledge's Madeline Reynolds spoke with Neela Gross, a Boston University PhD candidate in material science and engineering, to learn more.
Our lab focuses mainly on antimicrobial resistance, which that is basically when you get an infection in your body, right? So you get a cut and it gets dirty, and then you have an infection. When you go to the doctor and the doctor prescribes you an antibiotic. And so antimicrobial resistance is the phenomena where that antibiotic does not work because the bacteria are, for lack of a better term, resistant to it. It's a huge global health problem that I think our generation in particular is going to have to deal with. And already there are millions of deaths a year associated with antimicrobial resistance. And so we basically, our lab looks at specifically environmental contaminants that will make this phenomenon worse. And one of those are microplastics. So we know that they are ubiquitous sort of within our environment. So one of the questions that we had was, does this have a correlation or causation effect that will increase antimicrobial resistance?
So, how did you collect the data to study all this? How did you conduct the experiment?
Yeah, so I do want to be clear, it was within the lab. And so, in short, what we did was we put different types of microplastics. So there's polystyrene, which is what your packing peanuts are made out of, polypropylene, which is what you see those big crates made out of, polyethylene, which are like the plastic bottles that you see every day. And so we basically exposed bacteria, E. coli, which is another really common bacteria, sort of like in all shapes and forms. So we put E. coli with those plastics, and then we tested how much antibiotic it would take to kill the E. coli every 2 days. And so that's called the minimum inhibitory concentration, or MIC. So we tested this MIC every 2 days, and we saw over a course of up to like 10 to 15 days that this MIC, that the minimum amount of antibiotic you needed to kill off the population, increased over time. So we saw sort of in real time antimicrobial resistance increasing. And it was in a controlled environment within a lab. So those were the only two variables we were looking at. Obviously, in the real world, it's a lot more complex. There's more players, if you will, that are influencing these rates and whatnot. But it's a start. It elucidated quite a bit of material for us to use for further studies and whatnot.
So, in your research, antibiotic resistance is kind of the core of it, of course. So, how do microplastics contribute to this, and how many people die specifically from antimicrobial resistant infections each year?
That's a good question. So, antimicrobial resistance infections, they have direct and indirect deaths. And so, the indirect deaths, which basically means, you get an infection and then, you can't treat it. And so, it actually does quite a bit of damage to your body. But then the infection does go away eventually. But the damage to your body has just been too much. So, those are in the millions per year globally, of course. I don't know the number for direct off the top of my head, but those are also pretty high. I think the main point, though, is that both of them are growing numbers, right? So we see an increased number of deaths, direct and indirect, every year, which is sort of why scientists are alarmed. As it pertains to microplastics, what we saw was microplastics basically just provided a surface for the bacteria to attach to. And so bacteria have this phenomena where they produce what's called a biofilm. And the way that I like to describe it is that it's kind of like a house, and the bacteria can go into the house, and houses protect us from invaders. They protect us from weather. They protect us from anything that would want to sort of destroy us. So the same thing applies for this like biofilm and bacteria. They are much more complex than that, but like in short, that's sort of the deal. And so these bacteria, once they attach to the microplastics, they create this biofilm, which within the scientific community, we know that biofilms increase that MIC thousands of fold, so far past anything that would ever be used in the clinic. And so they're very, very, very bad. But you don't really see them in the body a lot. The only example I can think of are cystic fibrosis patients who get sort of like biofilm-esque mucus buildup in the lungs. It's a disease that's known for the antimicrobial resistance it produces and short lifespan. Yeah, anyways, so these microplastics, they grow these biofilms, and then all of a sudden we've got a huge problem on our hands because it's really difficult for bacteria to grow biofilms without a surface that they can grow on. They can do it, but it's much harder than if there was a surface. And as we talked about, how sort of ubiquitous these microplastics are, like within our bodies and within our world, it sort of gives them a surface wherever they go. What we found in the paper was really just the biofilm was sort of a phenotypic, sort of a physical production of the resistance that we ended up seeing.
What are some of the most common bacteria types as well as plastics that can lead to this antibiotic resistance in terms of how they kind of, attach to each other?
Yeah, what we saw in the paper was the type of plastic that was the worst for the antimicrobial resistance was the polystyrene. So that's packing peanuts. I mean, we only looked at two other ones, but there are many, many plastics out there. So, like I said, it was sort of just a study to kickstart this field almost in science. But I would say for bacteria, it really depends. So some bacteria like to attach, some don't. Some will only attach if others have already attached. So it really is quite dependent on what bacteria you have within the environment you're looking at. I would say lots of bacteria have antimicrobial resistance that are able to sort of produce resistance to antibiotics, and that's from genetic mutations that allow them to bypass or some of the mechanisms that those antibiotics attack or whatnot. So I would say antibiotic resistance when it comes to bacteria species is quite broad.
So, how do microplastics differ from other materials when it comes to contact with different types of bacteria?
Yeah, so we looked at glass as like sort of a control surface because we did want to see, like, as I mentioned earlier, when we came to this conclusion that there was this really big phenotypic physical difference in the bacteria that were with the plastics and the bacteria that were without the plastics. The ones with the plastics were just better biofilm formers. So if you took the plastics away from that culture, they'd still try and grow a thick biofilm wherever they were. So we wanted to see if this was just a surface thing in general, like if we put anything in there, were plastics unique or not? So we worked with glass a little bit because that's another contaminant within particularly like the makeup industry, glass beads, shampoo and face wash and all sorts of different things. And then it gets out into our environment. And so we found that glass, the surface of glass, just simply didn't provide the environment where these bacteria could grow these like thick alive biofilms. So on the plastics, they were able to grow this like big biofilm that was very alive. In the paper, there's an image that shows the two. So it's very green and very vibrant. But the glass, it was really patchy, so it wasn't covering the whole surface, and some of it was red, so it showed actually like some dead cells on there. And the glass also didn't have as high of antimicrobial resistance as the microplastics did. And so, yeah, that was alarming because not only did the microplastics have higher resistance, but we also know that there's lots of microplastics everywhere. While there might be some surfaces that could be better, sort of facilitating this resistance than microplastics, are they sort of spread out all over the world like the microplastics are? So, yeah, it was kind of like our comparison of different types of surfaces, plastic or not.
Where do we typically see microplastics pile up, and what communities are the most affected by microplastics and maybe even antibiotic resistance in this case?
You're going to see microplastics the most in areas that don't have very good waste disposal infrastructure. So, this is particularly the case in displaced people's camps. So, for instance, refugees and internally displaced people, when you are forced to move and set up camp somewhere that was not originally your home, particularly without an infrastructure, you're going to be exposed to a lot more waste than you normally would be because there's no, landfills or trash pickups on Thursday to like come get your trash and put it in a land and into a landfill or whatnot. And so, yeah, so these vulnerable populations are particularly at risk just because they are constantly exposed to these contaminants. And that is also so for microplastics, but it's also the same for antimicrobial resistance, right? Like we have wastewater treatment plants that, take all of the wastewater that we produce and it treats it and then allows us to reuse it in various different forms. Whereas low income areas in the world, and particularly in these displaced settings, they don't have that option. And so they're exposed to their waste and to pathogens that could lead to this infections that develop antimicrobial resistance. So it's sort of just like both at once. And so, yeah, that's something that our lab actually particularly focuses on because obviously it's not just a problem for them, it's a problem for everyone because we are running out of antibiotics. And so there will come a day when we're going to need other solutions. And so, what this work does, I think it lengthens that runway a little bit of finding solutions. If we can slow the spread, then we might be able to allow us more time to develop, novel antibiotics or other treatments that could help with these drug resistant infections.
Finally, what are you excited to research into next when it comes to this topic? You kind of alluded to that before as well, but just love to know once more.
Yeah. As I mentioned earlier, like obviously this is done in a very controlled lab setting. So we are super interested in taking this out into the field, and we have a great partnership with the Boston wastewater treatment plant. Probably have connections there and developing different protocols for extracting microplastics and testing them and the bacteria that might be on them. And we definitely want to do a little bit more of a mechanistic approach. So, like, we know sort of what is happening, but we really want to dig into why it's happening. And then, if we can do that, then potential solutions might pop up along the way. So there's a lot to do. It's kind of a huge, I mean, microplastics just on their own are sort of a huge field that's emerging. So I think we're all sort of scrambling to just see what is going on and then hopefully provide some solutions as we discover new things.
Neela Gross is a Boston University PhD candidate in materials science and engineering. Her research into the role of microplastics and antibiotic resistance is published in the journal Applied and Environmental Microbiology. She spoke with the best of our knowledge's Madeline Reynolds. Cuts to federal funding at colleges and universities from the Trump administration have generated questions and confusion from students and faculty. WAMC's Pat Bradley reports on a recent online forum held at the University of Vermont.
The Trump administration has canceled millions in funding for Columbia and Harvard, claiming campus anti-Semitism has not been addressed. At the same time, the Department of Government Efficiency, or DOGE, is gutting research funding across the nation, and the administration is taking steps to eliminate the Department of Education. In response to federal actions and uncertainty, the University of Vermont has formed 5 teams to recommend actions to respond to potential federal cuts. Acting Provost Linda Shadler explained the task force will focus on 4 key areas, including research.
In research, we are not seeing yet significant pulling of grants or terminations of grants or stop work orders on grants. We are seeing slowing in some of the organizations handing out new grants. When we look at our long-term exposure, we are actually pretty hopeful that we will be able to weather this time robustly. We have put together a small research stabilization fund, and we're working through how that would be distributed if needed.
Interim President Patricia Prelock reassured the campus that actions are being taken to address concerns.
Since 1791, we have been resilient. We've gone through rough times and really come out on top. So UVM will weather the storm.
Executive Director of Government Relations Wendy Koenig read questions submitted by the campus community. One, directed to Prelock, focused on student rights.
Has the university done any planning around protecting student demonstrators or activists?
This university was founded on the ability to express yourself, so freedom of speech is always an important component of this institution.
Koenig read and addressed a follow-up question on faculty rights.
It says many faculty feel that they have a moral obligation to speak out against unjust actions of the current federal government. What are your thoughts about that? It is everyone's individual right to speak out on actions that you find repugnant or abhorrent or problematic. And I think the great thing that has not changed about this country at this point is that we all do still have First Amendment rights.
A question on student researchers was addressed by Associate Vice President for Research, Sarah Cahan.
Will there be help to support grad students and postdocs if their grants get cut?
This is going to be a joint effort to help to provide bridge type of support for students to enable them to continue their degrees. Students should know that they're not going to be just left to the winds if dollars dry up.
Prelock advised caution as she responded to what someone should do if they see a student being taken into custody by ICE.
It is not appropriate for you to interfere, but you can certainly contact dispatch or the police services to let them know what you've observed. But you are not to interfere with it.
The University of Vermont has created a web page to keep the campus updated on federal actions, potential impacts, and planned responses. I'm Pat Bradley, WAMC News.
This has been The Best of Our Knowledge, episode 1800. The Best of Our Knowledge is a national production of WAMC Northeast Public Radio. Thanks to associate producer Madeline Reynolds. The latest on all National Productions programs is available via the Airwaves newsletter and our flagship station's website, WAMC.org. Until next time, I'm Lucas Willard.